I will start my presentation from where Eric stopped, that is about the nuclear fusion part. So the topic of my title is the fabrication of tungsten coated tiles for Indian Aditya upgrade Tokamak. Uh, Before my presentation, I would say few words about my center of excellence also. Uh, so our center of excellence is basically working in the field of plasma physics, where we are working on the basic plasma physics as well as the application part of the plasma. Uh, right now, I will deliver my lecture on the tungsten coating. But apart from that coating, our center is also working on the plasma application, mainly on agriculture, coal treatment, plasma nitriding, and different applications of plasma. So we have the active collaboration within our country with the Prime Institute for Research in Plasma Physics, that is Institute for Plasma Research, and the industrial application part of plasma physics. We have the collaboration with Indian Military Academy. Apart from this, we have the collaboration with the other Department of Atomic Energy Institute in India. These are my colleagues with whom I am working. Dr. Jaideep Ghosh and Dr. Amulya Sannyasi are from the Institute of Plasma Research from Government of India, and Dr. Jaideep Ghosh is the head of this Aditya upgrade Tokamak. So this was all about my center of excellence in my university. So now I shall start my presentation. The outline will be about the plasma, then what is ITER, then the probable material for target, then plasma assisted chemical vapor deposition, and about the system and result and conclusions. So as we all are aware that the plasma is an ionized gas and a mixture of positive ions and negative electrons with overall charge neutrality. This is also known as the fourth state of matter, and that conducts heat and electricity. And the main source of energy inside the sun is the responsible is plasma. The core temperature of sun is about 15 million degrees centigrade, and at this particular temperature, hydrogen nucleus fused to give helium and tremendous amount of energy which propagates through the sunlight through the earth. So for the creation of plasma in the laboratory, we use a technology that is called Tokamak technology. The Tokamak technology basically has the magnetic confinement, because we have to confine that plasma inside our reactor. So the basic strategy for confinement of for creating a plasma inside the lab is the magnetic confinement, then the plasma temperature, then energy confinement time, and the density. These four are the major aspects we must be kept in our mind while creating plasma inside a tokamak reactor. So the world economic, Russia, European Union, Japan, South Korea, China, US, and India are working on an ambitious research project that is called International Thermonuclear Experimental Reactor to achieve controlled thermonuclear fusion. Is one of the greatest challenge in the field of non-conventional power generation. And ITER is in design and fabrication stage right now. So apart from the cost and lifetime period, the important thing is that with the input of 70 megawatt power, we can get 500 megawatt output. But there are certain issues and problems that sustained and stable reaction. If these issues will be overcome by ITER, if technology works, then commercial reactor demo will be built for that. So looking towards the complete ITER, there are many thousands of components and working areas and fields are there. So we have concentrated the main work on the diverter part, because right now there are a lot of R&Ds is going on in the diverter part of the lot of tokamaks, not only ITER, but apart from ITER, there are other tokamaks. So all are working on the material walls and diverters. So basically, diverter situated at the bottom of the vacuum vessel, and the diverter extract heat and S produced by the fusion reaction and minimize plasma contamination and protect the surrounding walls from the thermal and neutronic loads. So during the operation, the heat flux sustained by the ITER will be somewhere around 10 megawatt per meter square in steady state, and the temperature will be somewhere around 10 kilo electron volt. So the tungsten with the highest melting point of all of the metals have been chosen as the armor material following an international research and development efforts, encouraging experimental results and successful prototype testing. In India, we have two tokamak. The first one is Aditya upgrade tokamak, and the second one is steady state tokamak. So recently, in the Indian tokamak, which was earlier a limited tokamak configuration, is now upgraded to Aditya upgrade tokamak, which has a diverter configuration. This is our Indian upgraded tokamak diverter reactor, whose head, Dr. Jaideep Ghosh, is also working with us at Center of Excellence in close association. So there were a lot of probable candidates for the diverter material and target material. But tungsten, we suppose that tungsten is the best one amongst the others because of some unique properties, out of which the highest melting point is the most important one. Then another one is it has a recrystalline temperature, and it has low fuel deuterium tritium retention capabilities. And the most important one is that the repairability with various plasma techniques, both ex situ and in situ, because most of the tokamak reactor has that facilities by default. So after each and every shot, we can again, without replacing those particular tiles from the reactor, we can coat them directly with that particular default techniques which all tokamaks have. There are different type of techniques for the tungsten coating, right from the PVD and then CVD and magneton sputtering and plasma spraying. And what particular technique we have concentrated is plasma assisted or plasma enhanced chemical vapor deposition technique, in which a chemical process used to deposit thin film from a gaseous state to a solid state in a substrate, and then chemical reactions are involved in this process, which occurs after creation of a plasma in a reacting gas. This particular plasma is generally created by two types of technique, either by DC glow discharge or by RF glow discharge or alternating glow discharge plasma techniques. So now question arises, why PACVD? Because PACVD has some unique advantages as compared to other traditional technique, what we have the PVD and CVD and magneton and other part. The first one is it has low substrate temperature. This particular coating techniques will be completed within a very low substrate temperature as compared to other traditional substrate coating techniques like CVD and others. It has a faster deposition rate. It has a energetic ion bombardment. The adhesion is also excellent. The step coverage is also good as compared to other techniques. It has the increased density of deposition, and after this complete coating, we can easily clean the reactor by creating hydrogen plasma inside the plasma chamber. So it can be cleaned easily as compared to our other traditional techniques. And as I mentioned, that PACVD is preferable because in situ coating in fusion reactor is possible because each fusion reactor has plasma glow discharge facilities. So this one is the particular setup in my center of excellence. We have a vacuum chamber of 30 per liter capacity, whose electrodes are around 200 millimeter, and to create a vacuum of 10 to the power minus 6 millibar, we are using a combination of rotary pump and a turbomolecular pump, which is a corrosive resistance turbomolecular pump. Then we have DC power supply and RF power supply of the 13.56 600 megahertz to create to ignite that particular gas with to create plasma. We are creating hydrogen plasma and the WF6 as a precursor gas what we are using, and we can also monitor the reactive species inside the plasma at the volume of at the vacuum of 10 to the power minus 3 millibar and onward. With this particular QMA or the residual gas analyzer, we can exactly see the online monitoring of the reactive species, what is happening inside the vacuum chamber. This is a pictorial view of our experimental system, what we have developed from the grant of Department of Atomic Energy, Government of India. We received a grant of almost rupees 2 lakh USD from Ministry of Department of Atomic Energy. So what we did basically, we create a good vacuum with the help of a combination of rotary and turbomolecular pump of nearly order of 10 to the power minus 6 millibar. What particular substrate we are going to coat is the graphite. We have a neutral gas to assist plasma production, that is hydrogen, power supply, and the precursor gas. And this particular reaction, what we are doing, the ratio of hydrogen and tungsten hexafluoride gas is 95% to 5%, and the creating RF glow discharge plasma. Because of that, the HF will pump out, and this tungsten will be deposited on that graphite sample. So before our coating, we have created DC glow discharge plasma and RF glow discharge plasma, because we have to characterize our plasma, that what is the temperature and what is the density of our plasma. So we have characterized our hydrogen plasma with the help of Langmuir probe, and with different powers, right from the 25 watts to 500 watts, and depending on the parameter, we were able to calculate the density of that glow discharge plasma, what somewhere around 10 to the power 16 meter per minus, and the electron temperature was nearly around 2 electron volt. And the most important thing, we did this all this thing to have a suitable coating area, because of our the diameter of our electrode inside our vacuum chamber is 20 centimeter. So we were able to see with the Langmuir probe that with the different variation of the power, we were able to get a uniform density in the region of somewhere around 16 centimeter, so that a sample can be put in between that particular area, so that we can have a uniform coating. And then another spectroscopy technique were also tried to get the confirmation of the electron density and the electron temperature using the vibrational bands and optical spectroscopy. So we were also able to confirm that we have the H alpha and H beta ratio in the same manner what we are getting in the other traditional Langmuir probe method. So now moving towards the coating on graphite with the tungsten, we again had the same process. We created a base pressure of 10 to the power minus 6 millibar. Then hydrogen gas was filled to reduce that particular pressure up to some part. Then we fill a 5% of the tungsten hexafluoride, and the total coating time was 120 seconds. We tried with different times and we tried with different powers. So this one is the what we have received. The optimum one is the 125 watt and 120 watt. If we increase the power, or if we increase the coating time, then there is itching and there are other issues also. So and these are our samples what we have kept on K-type thermocouple to remove the impurities and the moisture present inside the sample. So we heated that sample with the 200 degrees centigrade, and this one is the particular diagram of the tungsten hexafluoride and hydrogen gas in a combined part. So as you can see that we coat tungsten on this particular graphite sample. This one is the uncoated and this one is the coated sample. And as I earlier mentioned that we are using a residual gas analyzer which give us the online monitoring of the reactive species inside the vacuum chamber. So the tungsten hexafluoride gas was completely dissociated with the hydrogen. It can be clarified with this particular residual gas analyzer diagram. And then we did different types of coating and other varying power, pressure, and vacuum and different. So we were able to get a good amount of coating on the different types of samples. So the coating thickness was somewhere around 1 to 1.5 micron or above that also, but that particular coating was not uniform. So right now we have a coating of tungsten on graphite sample of the order of somewhere around 2 to 3 microns, and now we are further working to increase the uniformity part. And there are other evidences of the EDX. Through EDX, we have also come to conclusion that there is a coating of tungsten on the graphite sample. And this one is the particular tiles that the Indian Aditya upgrade Tokamak has. We have successfully coated with the different dimensions. We have successfully coated this particular tiles to the for the Aditya upgrade Tokamak, and this particular tiles we have sent back to the coordinator of that Aditya upgrade Tokamak, and they are going to test it. So in short, I can conclude that we were able to because creating a tungsten hexafluoride gas plasma was very difficult with that much percentage also. So we have successfully produced that particular because no ready available data was not available anywhere. So we have the data collection of this tungsten hexafluoride gas and plasma with the help of hydrogen and calculated density and the electrode uniform coating we can have on 15 centimeter, and the tungsten coating was also 95% pure, because purity is most important part in case of fusion, because of there might be chances of contamination. Of course we are not sure about that part also. We are working on that, we have to work another part also, but as for the evidences we have the reduced amount of that C carbon and the hydrogen and fluorine part. And we have characterized our sample with the help of EDX and SAM and SIMS also, and we have able to find out that the coating rate was somewhere around 600 nanometer per hour. And the important thing is that now we have given this particular tungsten coated tile to the Indian Tokamak. So the test result of the coatings in real Tokamak environment, such as coating stability, flaking, or melting threshold for different coating will be tested. We planned in 2019 January, February, but because of this COVID and lockdown, we shifted to till now. We are not able to get the result of from the tungsten coating with the help of Aditya upgrade Tokamak. These are our some publications during that particular project work in what we are doing the coating part in the Center of Excellence. And now we have started working on the graphene coating on stainless steel also. I have discussed this particular issues with my colleagues at the different laboratories that we can have this type of coating with the, of course, we have this type of coating with the CVD techniques, but we can try with our plasma assisted chemical vapor deposition technique also with a low substrate temperature with the help of methane and hydrogen plasma. And then we can have the initial diagnostics with the help of SEM and other EDX and Raman spectroscopy. So we are in a process to work on this particular graphene coating on the stainless steel part. What we have, we also want to work with this particular area. I would like to thank my funding agency, my management, my vice chancellor, my colleagues, my friends, and the organizer, Dr. Philip, for giving me opportunity to present my this amount of work. We have started this particular work in from 2016-17 onwards, and we have established a center of excellence at our university. So thank you very much. Thanks for your kind attention. Thank you.